We start our final presentation in the series looking specifically at microprocessor-based controllers. To recap from the last presentation, a microprocessor by itself is not a computer. To be functional, the microprocessor must be connected to other integrated circuits that provide the memory and the I/O capability. A microcontroller is a computer on a single IC, designed specifically for control applications. It consists of a microprocessor, memory, both RAM and ROM, I/O ports, and possibly other features such as timers and ADCs or DACs. Having the complete controller on a single chip allows the hardware design to be simple and very inexpensive. Microcontrollers are showing up increasingly in products as varied as industrial applications, home appliances, and toys. In such uses as these, they are called embedded controllers because the controller is located physically in the equipment being controlled. The main difference between microprocessors and microcontrollers is that microprocessors are being designed for use in microcomputers with greater speed and larger word size are the driving requirements, whereas microcontrollers are evolving towards reduced chip count by integrating more hardware functions on the chip. Most control applications do not need the 32 or 64-bit word size and 4 GHz speed of the newer microprocessors. 8 or 16 bits and 1 MHz will work fine in many applications, and the single-chip microcontroller costs much less. Another difference between microprocessors and microcontrollers concerns the instruction set. The microprocessor tends to be rich in instructions dealing with moving data into and out of memory. The microcontroller has fewer memory move instructions and more bit handling instructions. The reason for the lack of memory move instructions is that the microcontroller typically has only a small amount of RAM, which it uses only as a scratch pad. The additional bit handling instructions were included because they were so useful in control system applications. For example, in a control system, each separate bit of a parallel output word might control a separate device, such as a motor or indicator light. The bit handling instruction allows the software to turn one device easily on or off without affecting the others. There is a vast array of microcontrollers available. Whilst not always infallible, there is a good breakdown of available microcontrollers on Wikipedia. We will review a few of the older microcontrollers as they are still in use, if not in manufacture, and they demonstrate the concepts simply. We will look at two different microcontrollers, the Motorola 68HC11 and the Intel 8051. The Motorola 68HC11 is a popular 8-bit microcontroller that has 256 bytes of RAM, 8K of ROM, and 512 kilobytes of EEPROM. It also has 5 8-bit ports with built-in serial data transfer and ADC capability. This chip was introduced in 1984 by Motorola, but is now manufactured by NXP Semiconductors. Another popular microcontroller was the Intel 8051, which has 128 bytes of RAM and 4K bytes of ROM, 4 parallel data ports, and a serial port. For control applications, these hardware arrangements usually are adequate. Generally, the mode of operation is similar, but there are some specific differences for certain chips. Generally, ROM is used to store the control program, and RAM is used as data registers and scratch pad. The I/O signal lines are usually connected directly to the microcontroller without additional port circuitry. Software is typically written in C, Python, or JavaScript, or some other language, including assembly language, and then converted into machine language with a compiler or assembler program. The machine language program would then be loaded into the microcontroller's ROM or EEPROM. Single-board computers are off-the-shelf microprocessor-based computers built on a single printed circuit board. They came in many configurations, but in general they use a standard microprocessor such as the Zilog Z80, the Intel 86 family, the Motorola 68000, or a microcontroller. They also include memory ICs, both RAM and ROM, I/O capability, and perhaps special interface circuits such as ADCs or DACs. The obvious advantage of using a ready-made microprocessor board is that it eliminates design and board testing time. This is particularly important in small volume production or one-of-kind systems. A programmable logic controller, PLC, is a self-contained microprocessor-based unit designed specifically to be a controller. The PLC includes an I/O section that can interface directly to such system components as switches, relays, small motors, and lights. Developed in the late 1960s to replace relay logic controllers, PLCs have evolved to be able to handle sophisticated modern control applications. The main difference between PLCs and other devices discussed in this section is that the PLC has the microprocessor, ports, and power supply built into a package that has been ruggedized for an industrial environment. Installation is very easy because in many cases, the sensors and actuators can be connected directly to the PLC. Once installed, the microprocessor program is downloaded into the PLC from some source, such as a personal computer. The PLC manufacturer usually supplies software to facilitate the programming operation. This software allows the user to write a program with line-by-line instructions, or it can convert a relay logic wiring diagram, or ladder diagram, directly into a PLC program. Multiple PLCs in a plant can be networked, so the individual units can be monitored and programmed from a single station. This is a form of distributed computer control, DCC, discussed in Chapter 1. The PLC has become the stalwart of industrial automation. Mastering the PLC will greatly assist your automation careers, so we will spend a fair bit of time on PLCs in course and lab work. We will come back to the other components of control systems, but we will initially focus on PLCs, so the lab work will be more relevant. But before leaving our review of microprocessor-based controllers, we need to look at the role of PCs in control systems. The availability of relatively low-cost, off-the-shelf personal computers, or PCs, has made them an attractive alternative for small, one-of-a-kind control applications. Control system software packages are commercially available for the PC that run under DOS, Windows, and Linux. These programs are adaptable and allow the user to tailor the software to fit the control application, essentially turning a PC into a PLC, although not as rugged. Most of these packages use interactive graphics to link animation with changing process values. Some programs have provision to mathematically simulate the process being controlled to help optimize the controller coefficients. There is some skepticism by some clients as to the reliability of PCs, so often clients would prefer to specify PLCs rather than PCs. A standard PC comes with expansion slots, which are circuit card connectors emanating from the motherboard or mainboard of the computer. Expansion cards plug into these slots and form a bridge between the computer and the outside world. Many different types of interface cards are available, such as I/O serial and parallel data ports, ADCs, DACs, and computer-controlled output relays, to name a few. Historically, data acquisition and control functions were kept separate. Controllers ran the process, and other instruments measured and recorded the results. The concept of having a single PC perform both tasks seems logical. After all, the PC can use its computing ability first as the controller and then tabulate systems performance data. These data can be stored on disk and/or displayed on the monitor. A potential problem may arise because the controller must operate in real time. If a computer is to control a process and monitor it at the same time, the data reduction process must not take so long as to interfere with the control duties. A control response can't wait. One way to overcome this problem is to divide the control and data acquisition tasks among multiple processors. Using the PC as the master computer, a separate microprocessor on an expansion card can perform data collection uninterrupted. One type of I/O controller card has slots for 3 smaller boards. These smaller boards have various combinations of analog and digital I/O ports and counters and timers. Some boards are available with solid-state relays, which can be used to directly control AC and DC motors. A PC with I/O expansion cards often costs less than a standalone computerized control system. The cards do not need a separate enclosure and use the PC's power supply, keyboard for input, and monitor for display. Also, using a standard PC means that programs can be developed on another computer, eliminating process downtime. Numerous manufacturers are selling rugged PCs that can survive in harsh industrial environments. These computers typically use a membrane-type keyboard. The keyboard appears as one continuous sheet of flexible plastic, and have sealed cases and filters covering the air vents. Some models of these computers are rack-mountable and contain their own battery backup power supply. This brings us to the end of the second chapter. There is a summary presentation to follow.